Hi guys, I'm gonna give you more information the on the solar luminescence. Well, this song turning into lights, and it tells guy you have a whole channel on that. So I'll show you a video, and in the description I'll put a link to his channel, so you can subscribe to his channel and you can get all the information. And no, he's not a flat earther, but he have some really good videos on how to create song, how to make song turn into light using water bubbles. So this is just in case if anybody curious about turning song into light, and that's all.
Hello, my name is Brett Gibson. I am an undergraduate general science major at Western Washington University. This spring quarter of 2011, I took on the challenge of demonstrating and investigating single bubble sonoluminescence. And I'm happy to report some success. Here it is, light from sound. What's glowing is a tiny air bubble trapped and driven to repeated cavitational collapse by intense ultrasound. I took this image with a 1-minute exposure after a brief red light exposure to get the flask image. This is to show how tiny and dim the glowing bubble really is. It's not that distracting little light there that just faded. Just look at the center. Keep looking. Do you see that little twinkle? That's the glowing bubble. Here's a 2-minute exposure. You can really see the glow. Here's the resonator I used with the lights on. It's a simple 100 milliliter Pyrex round bottom boiling flask, and the fluid is just degassed distilled water. This is a schematic of the experimental setup. The function generator provides the ultrasonic frequency, which gets amplified by an ordinary audio amplifier. The signal drives the piezoelectric transducers glued to the flask. They're kind of like speakers. The transducer on the bottom acts as a microphone to measure the amplitude of the flask's response. The variable inductor tunes the circuit for impedance matching. That way, the transducers get maximum voltage, around 700 volts when I'm driving the flask at resonance. The trapped cavitating bubble makes ripples on the microphone transducer oscilloscope trace. This is about 2.5 volts peak to peak. I increase the amplitude cautiously to around 4.5 volts peak to peak. Here, the bubble should be glowing. There's an abrupt threshold if I go too far. The bubble is destroyed and the ripple disappears. Besides taking pictures, I did manage to gather some data. So here's a laser pointer aimed at the bubble. After intersecting the bubble, the laser beam goes to a photodiode, which measures the intensity of the beam and passes that information to an oscilloscope. So as the bubble gets bigger, it blocks more light, and the intensity goes down. In other words, the intensity of the laser beam at the photodiode is inversely proportional to the bubble radius. Here's an oscilloscope trace from the photodiode. Like I said, the signal is inversely proportional to the bubble size. There, I flipped it over. This shows the bubble expanding, then collapsing rapidly, followed by some after bounces. Here's some high-speed video of that bubble motion with expanding, collapsing, and after bounces. This was made by Dr. Tom Matula of the University of Washington. Here's one period of the bubble motion. It looks like the bubble goes from its maximum radius to the minimum in just about 4 microseconds. And somewhere at that minimum radius, light is emitted. Brad Zeiger of the University of Chicago sent me this plot, made with a photomultiplier tube, which is more sensitive than the photodiode that I used. I include one of my oscilloscope traces for comparison, and to the eye at least, it looks like there's good agreement in the bubble dynamics. Here's the photodiode signal again, corresponding to the changing bubble radius. The drive signal, shown superimposed, is directly proportional to the acoustic pressure inside the resonator. This plot measures bubble radius and acoustic pressure more directly. Again from Dr. Matula of the University of Washington. Notice how the minimum pressure leads the maximum radius by about 9 or 10 microseconds. That matches my measurement pretty well. Well, that's it for this quarter. I hope to study single bubble sonoluminescence more in the future. There is much more to learn and explore about this mysterious and delightful phenomenon.